Okay.
So
Good afternoon and welcome to our first food4Rhino webinar in 2024. Today, Matthias Fuchs is with us and he's going to talk about TRmesh and TRfem, volumetric applications in geometry and simulation. TRmesh is a new Rhino plugin that generates the tetrahedral meshes, also known as unstructured grids, in a robust and performant way. So Matthias will show what the plugin exactly does and how it works and what are the workflows. And I think also how it can be combined with the new Shrinkwrap function in Rhino 8. And Matthias Fuchs is a mathematician with a very ample experience in applied geometry, statistics, and simulation. He has been senior researcher at Saha, at Code Group, and now he's an independent programmer specialized in numerical algorithms and for geometry and in Rhino. And yeah, I hope you will enjoy this webinar. Please feel free to use the chat on the right side of your screen. I will collect your questions, your comments, your feedback, and then in the last 10, 15 minutes of the webinar, I will pass all your questions to Matthias. Remember also that this webinar is being recorded, so if you miss any part of it, you will always be able to watch it on our YouTube food4Rhino webinars channel. So, Matthias, thank you for being here again with us, and we are eager to see your advancements in TRmesh.
thanks, Carlos. Well, and thank you for organizing all of this. I really appreciate the effort you put into this. So yeah, welcome to a new TRmesh TRfem session. TRmesh is growing at a very healthy pace. In other words, everything takes ages, but it's still alive. And I think it has a really nice, really cool new feature, even so things really go much slower than I hoped. But it's definitely, there's just one direction. It will just grow and keep on growing. And I can't stress it enough. I really depend on your help to make it grow. But let me demonstrate a bit what everything is about. So what am I going to talk about? Well, first of all, I will go through the original motivation again, which is topology optimization. So this is which is what drives me as a finite element guy. Then I will talk about a bit, I will mention the thermal side of things a bit, but not too much. And then I will advertise the idea that 3DM, the 3DM file format, can also be used to store truly volumetric information. So BREP is the boundary representation, but sometimes you want to store things like temperatures, stresses. Sometimes you want to view things just as a volume. And the core novelty here, so this is the kind of spoiler alert, but if you don't take away anything from this webinar, one thing that you please take away is what I want to do is put volumetric information into the 3DM file format itself so that you can share it without any hassle or circumstances. I will do some demos, and I will also demo a bit Delaunay's side of things, and I will demo a bit how to drive TRmesh from Rhino itself and from Grasshopper, because that differs a lot in several aspects. So I think I should first show you where all of this is going before I start with the official motivation here, right? Because you probably want to see the important parts first and not wait for an hour until I show the more interesting things here. So let's try to look at our model here that comes from Spherine. Let's make this. This is a very nice minimal surface here. And let me now turn on a Grasshopper document here. I will later on go through the whole Grasshopper document and show you what's going on. But as you can see, the Grasshopper document added layers around the mesh, all right? So we had this white mesh here in the middle. I think X-ray is best. So here, now you can see it. And you see this is a very intricate geometry here. What kind of geometry is this? Well, this is a heat exchanger. And heat exchangers exchange heat the best when they maximize an area. And for some funny reasons, it turns out that minimal surfaces, even though minimal surfaces minimize an area, are very good at this, at generating space-filling surfaces, a bit like Hilbert surfaces, okay? But that's a very remote analogy here to just explain what's going on. So this minimal surface here in the middle is just a minimal surface I got from the great guys at Spherine, and it's supposed to, it's the middle wall of a heat exchanger. So there's one side of this mesh is a cold side and the other side is the hot side. And now imagine we want to give our heat exchanger a thickness, and that's where Shrinkwrap comes in. Okay, so we can extend this mesh to both sides to give it some thickness. But imagine just pretend we are engineers and say, okay, the inlet, the tubes, the whatever, the places it's fixed on should not be subjected to the Shrinkwrap. Okay, so you only want to Shrinkwrap parts of the mesh. And this is the main geometrical application of TRmesh. And let me demonstrate this. So first of all, I will show you how TRmesh, in a way, does something very similar to Shrinkwrap. So we have here several layers with a thickness, okay? So maybe I should show you a part of that Grasshopper document here. So we have some ISO values of a thickness. And I'm just drawing 3 layers here. I might as well draw 10 or 1 or none at all, but I just have 3 here because it's funny. So as you can see, we are isosurfacing a certain distance field from our initial mesh, all right? And then, because we want our life to be colorful, we are hitting this with a color gradient, and the color gradient just encodes the difference, the distance from the initial mesh. Okay, so I hope this is more or less clear what's going on here. We just have 3 meshes that give the initial mesh a thickness. And the nice thing here is, well, it's incredibly fast, even though this is volumetric information here. Well, it just took 35 milliseconds. So it's at absolutely interactive speeds. You don't need to wait overnight, okay, for this to happen. You can just play with it immediately. This is not using Shrinkwrap, but it's very similar to what Shrinkwrap is doing, but it's not based on a voxel engine. It's based on a TRmesh. And in what respect does it enhance Shrinkwrap? Well, the nice thing about TRmeshes is that they are incredibly flexible. So here in this case, I take, well, there's a distance to the mesh, and we can modulate the distance field that is isosurfaced here. And let's demonstrate this. So there are 3 parameters here. Alpha is the strength. And this is the main message here, okay? So we can modulate locally the distance field. So if you ever had the desire to say, okay, we want to shrink wrap only a part of a mesh and not everywhere. Or for instance, well, some parts of the geometry are just fixed. You don't want to mess with it, or you don't want to modify it. Then this is for you, okay? So here I am sliding the center along the x-axis of my constraints, which are applied on top of the signed distance field whose isosurfaces are being taken. And I hope you can really see what's going on here. So I will just spin the whole model a little more so that you get an idea. Well, as always with three-dimensional stuff, it's always difficult to visualize it in the right way. If I had a section tool here and slice through everything, I think one wouldn't see much. So I strongly believe that setting just the right amount of transparency is always the right, or is the best. Well, not always the right, but it's kind of the best way, because that's how our brain works. Of course, not too much transparency and not too little. There's just a sweet spot where our brain can just see how these layers here are layers of different thicknesses around our initial mesh. So I think this is a pretty cool functionality, and it's not at all something that is supposed to replace Shrinkwrap, which would be hopeless anyway. So everyone loves Shrinkwrap, and it's awesome, it's great. It's just something that perfectly fits to the concept of Shrinkwrap. So if you want to apply this workflow to, say, an engineering part, then ideally you apply Shrinkwrap to an initial mesh around, to obtain an initial mesh around your ground truth mesh. And then you apply this methodology here, the TRmesh methodology, to the closed volume that you obtain by Shrinkwrap. All right, so that would be the perfect way to apply this. All right, I hope you see what's going on here after me here playing with the sliders again and again and spinning our model here. Maybe from this perspective, it shows you the best how actually this effect is achieved of setting the thickness in a variable way. And as you can imagine, this is incredibly powerful, because now the one slider of Shrinkwrap, now all at once, can be set anywhere from a model where you need it. Here it's thicker, they're thinner, there are no Shrinkwrap at all. So this is incredibly powerful. And I think this is really cool. You should check this out. All right, so this was the main message. And now I can relax because I brought the main message across of that webinar. And now I can start from scratch again. All right. So first of all, I placed the 3D file and the Grasshopper file that I'm showing you here on a website. I placed it on this website here. So if you're very motivated, you can follow along here. It's this 3D file and this GHX file. Cedric.com, webinar, TRmesh, TRfem. If you want to follow along, it should just work. And if it doesn't work, please tell me. But it should. I think it does. I tried it on several computers. All right. So in order to be a little organized, let me start from scratch. How do you get TRfem and TRmesh? So there is this website here called food4Rhino. You click download, and then if Rhino 8 is open, you will automatically direct it to Rhino 8 and can install it here. And the same with TRfem. If you're still on Rhino 7, then you only get the version 2.90. So the newest version that I'm talking about is a Rhino 8 version only. Why is that? Well, in principle, there could be a Rhino 7 version as well, but I just encourage you to update to Rhino 8. In particular, there's still the promo period, I think until end of February or so. So take advantage of it. Rhino 8 is just awesome. So just get yourself the latest version. It's absolutely worth it. And I'm talking about Shrinkwrap all the time. So if you're interested in that, I guess you probably already have Rhino 8. That being said, if you are really stuck with Rhino 7, well, you can still run the older versions of TRmesh, TRfem. The versions up to 2.90 will still work on Rhino 7. Now, if you're on a Mac, I'm sorry, guys and girls, this is a considerable overhead. It's in principle possible to write a Mac version, but I guess I will have to charge something for it because it's just a considerable overhead for me to do it, and it's not going to happen unless there's some additional a little help. Well, so enjoy. I hope you're on Windows 10 or 11 and have Rhino 8, and I'll assume that for the rest of the talk. All right, so if you absolutely forgot your login here, then if you don't tell anyone, then you just use the package manager here, okay? So, but don't tell anyone. So why don't I like this? Well, because here you don't have to give me your email address. On food4Rhino, we will get your email address, and then in half a year, I might write you an email. Hey, did you like it? What's going on? Do you have any suggestions? So this is just I will just write a friendly email asking you how you liked it or not. I think that's very fair. And I think it's fair that you give us your email. So the longer you, the more you use food4Rhino instead of the package manager, the more likely it is that TRmesh will stay for free. It's not going to stay for free forever, but for now it costs 0.0, so enjoy it while it's still possible. And the more you give me your email, the more probable will be that it stays there. All right, so this is how you get TRmesh. Let's now step back a little more and go back to the original presentation here and turn off this for a while. All right. So, and the same is valid for the discourse category here. So for any kinds of questions, remarks, and hopefully constructive criticism, please put everything here on that discourse topic, TRmesh. So I'm not using the layer book because I don't want the default layer to be off. Maybe there's a trick to avoid that. So as I promised, what is the history of this whole subject here? How did all of this get started? Well, TED meshes are what you need for finite element analysis. And I think I will just devote, well, at most 5 minutes to that, probably less, because if you do finite elements, then you know you need a TED mesh, so I don't need to convince you. And if you don't yet do it, then I don't have enough time to convince you. Some people do finite element analysis without TED meshes. Maybe then it's no more called FEM, but maybe then it's just called simulation. It's possible, but why does TED meshes have this bad reputation? Well, first of all, because they are large and because they're difficult to generate. Well, they are large, okay, but later on I will show you 2 million is not a problem for TRmesh. So It's 2024. It's not a problem anymore to deal with 2 million tetrahedra, right? So I think this that objection was valid maybe 10 years ago, but in 2024, this has basically disappeared with the latest hardware. And the difficulty to generate a TED-mesh, well, I hope I can convince you that TRmesh is really easy to drive and really fast. So this is a paper here in which I picked the lowest hanging fruit. So what's the easiest finite element analysis? Well, it's the heat transfer. So in this paper, I wrote down the whole story of heat transfer and how to set up a complete finite element tool chain just from nothing. So I wrote it all up, and it should be, you can follow this just with high school mathematics. And I'm very indebted to Miss Yingying Yan from Carnegie Mellon, who kindly shared her experiments with TRmesh, in which she computed the heat loss for bricks and did a lot of nice experiments here with TRmesh TRfem on how to minimize the heat loss. So this is the opposite to the heat exchanger. The heat exchanger tries to maximize the heat flow, and here we try to minimize it. It turns out that actually the best geometry here and would actually be another Hilbert curve. So if you filled the brick with a very long curve, and if you assume that the air in between was a perfect insulator, then the longer the structure in between is, the longer the path will be that the heat has to travel, and therefore the higher the insulation will be. Okay, so that means we have to apply more constraints in order to turn this into a realistic optimization problem, but it can be done. And if you feel like pursuing these experiments here, yeah, well, just go ahead. I will show you in the corner here. So just that you see. Oops, didn't want to do that. A little finite element analysis here. Well, I'm doing this in Rhino 7 so that I don't get too confused, but yeah, should work just the same. This Grasshopper document here is on the example side on Cyric.com and then examples, and you get there from the main TRmesh TRfem site. And let's set here the target TED-mesh length to the maximum value. Let's keep our fingers crossed and enable the solver. There we go. So as you can see, the geometry here is the corner, the outside is cold and the inside is hot. Then you can see the TED-mesh here. These are the gray edges, and then the hot interior vertices are marked with red dots, and the cold exterior vertices are marked with chili blue dots. And this huge, well, it's not that huge, but this Grasshopper document here, well, what does it do? It just applies TRmesh. Well, actually, the old component here, it applies the old TRmesh component from a closed solid mesh, and then it applies TRfem somewhere down the line, and then as always, well, it just hits it with a color gradient and then previews the meshes. That's all that's happening here. And by the way, this also works on shape diver. That I'm not going to have a lot of time to go into the details here, but what I want to show you is how fast TRmesh TRfem is. I don't know if you have any experience with, say, Abacus or ANSYS or whatever other tool there is, but I challenge you to show me a way where you can do a finite element analysis in real time. Just draw the slider and you get all the results. You get the meshing and the finite element analysis at the same time. And as a math guy, this is incredibly satisfying here to watch, because we see that the transition from the discrete realm of tetrahedra, which are just finite boxes, well, not boxes, but yeah, finite polytopes, four-sided polytopes just hammered together, to the realm of smooth, infinitely smooth surfaces, that we can watch this transition happen live. So as I drag this slider here and decrease the target edge length, we see how the solution to the thermal problem gets better and better and better and better. And the solution is computed on all these blue dots here, okay? So on the vertices, that's where I compute the solution to the temperature field. And as expected, the temperature field grows from outside to inside. All right, and it's a smooth surface, and the temperature field is just sampled on these vertices, and then it's interpolated along the tetrahedra. And the nice thing here is, you think it looks incredibly smooth already, even though the TRmesh is still very coarse. But as you can see, the interpolation is just linear on the TRmeshes. So on every tetrahedron is just an affine plane. So even though this interpolation method here is not quadratic, it's not some fancy dual contouring and so on. It's just an extremely simple cutting the tetrahedra along linearly interpolated isosurfaces. The result already looks extremely nice and smooth. All right, so yeah, you can try this example out with Rhino 7. It should just work straight from the download side, from the example download side. All right, so this is the end of me talking about finite elements for today, because as I said, finite elements is probably something that you either already do or that I can't yet convince you to do in the small amount of time. So what's not so well known about TRmeshes is that they are incredibly useful for purely geometric tasks as well. So if you dislike physics, and if you dislike simulation, if you dislike finite elements, for whatever reason, then they are still incredibly useful. So, oh, sorry. I'm still not done with finite elements. Let me just add these two slides here. Sorry, forgot about these two slides. So if you do topology optimization and you have this feedback loop, say between ANSYS and Rhino, where you remove the excess unused material to make the process lighter. And this is becoming extremely important because all these novel additive manufacturing methods make this workflow even more possible. So you can basically, nowadays, you can print anything. These 3D printers have become so good that this is no more just a theoretical possibility. You can topology optimize almost anything. So this feedback loop is very cumbersome. It runs overnight, and it's a horrible mess to do. Error handling here in this feedback loop. So what I want to say is that TRmeshing should be done in Rhino itself, because it's geometry. A TRmesh is just angles. It's just, this is what Rhino is good at, and ANSYS should just do what ANSYS is good at, namely the physics. So if you have the TRmesh on this side, then you can export the TRmesh directly in the file format. Whereas here, you have to manufacture your own file format because the compartments of the solids form a non-manifold mesh, right? Just for geometrical reasons. And there's no good file format for this kind of stuff. And then you have the metadata on top of that. You kind of have to manufacture your own file format, or you have to write your own exporters and importers. So this is a mess for so many reasons, and this is the basic problem that I wanted to solve with TRmesh. So here I'm saying, okay, you can export the TRmesh just in, say, Gmesh or whatever. But what I'm going to say now with the new version of 2.91, you can even use 3DM. And that makes this step even easier, right? So if the export just happens in 3DM, well, then well, yeah, okay, then one needs maybe an importer for TRmeshes, maybe for ANSYS, but apart from that, everything stays in just one file format. That's incredibly easy to do, and a huge improvement over the old topology optimization workflow. All right. Okay, but now I'm done with topology optimization and physics. So now I want to advertise the more geometric usages, use patterns of TRmeshes a little more. I will show you how 291 can generate also just pure Delaunay meshes. I'll do that in a second. But what is the basic geometric usage? Well, it's thickening, okay? Thickening is a very common thing to do in Rhino. There have been so many Rhino plugins, and they're all awesome. You should check them out. I think the first, no, I'm not sure which one was the first one, but there's Multipipe, there is Dendro, there's Exoskeleton, there is Weaverbird, there's Pufferfish, there's Kangaroo Physics, and they're all awesome. Extremely cool. You should check them all out. One thing that all of them do, well, they do a lot of things, but thickening is a basic task in Rhino. So either you thicken curves because you want columns, or you thicken surfaces, well, for construction reasons, or whatever, but it's just geometry, okay? That's not a physical task. So the main but why do I get the package manager? So the main problem comes when you want to thicken a geometry and you want to share it with a coworker. Then it's a problem, right? Because you can just either bake all those isosurfaces as a mesh into the document and then send it along. But then what to do with it, right? So then it's not thick enough, then you need to modify it then all over again. So what you do, in the end, you have to then tell your coworker, well, then also install all the other plugins. But then, no, it doesn't work. Then you have to write emails forth and back. So as long as the volumetric information is not part of the 3DM file format, all you can do is either send all the plugins along and say you do it yourself, or you export the isosurfaces as meshes and then send the mesh to your coworker. So, but if the plugins don't work on your coworker's computer, well, what do you do then? Well, just ship the computer, right? That's the easiest thing. So I should not tell you how much time I wasted with Del E just to make this admittedly very lame joke here. So if you don't want to just ship the whole computer, then what do? well, how do we put the whole TRmesh into the document? And now here comes the new trick that makes TRmesh such a fast and new isosurfacer. The trick that I'm doing is that I put the whole TRmesh, so the whole volumetric information, just into one single ON mesh. So if you are a Rhino developer, then you know the user data mechanism where plugin developers are allowed to attach their own plugin formats data to the CDM file. And this is how TRmesh worked until 290, but from 291, I don't use the user data anymore. I just hijack, or you can also call this a hack. I just hack the CDM file format and put everything into the ON mesh. How do I do this? I just abuse the 4 indices of the mesh face for the tetrahedra. Now, this is a really bad hack, but it works, and it even gives valid meshes. And it gives a lot of benefits, because then the transforms work, so you can just hit a mesh with an affine transform, and then you transform the TRmesh, and so on. So maybe mesh booleans don't work, but well, this is an incredibly simple but very powerful trick. All right. So that's the presentation here, and in the remaining 10 minutes or so, I should just do some actual meshing here. So I'm running a bit out of time, but one thing that I do want to show you is let's just do some very basic TED meshing here, whatever silly solids we have. I do want to show you the old interface that still works, and I'm just going to show you how to export the new TRmesh format from this one. So you can turn on the panel either with the menu, which is just now is hidden. There it is. Okay, so it goes away. Here, show hide panel, but I recommend you just use this little gear icon here, and then show panels, and then turn on TRmesh down here. Okay, that's I think the easiest way, and then it will just fit here if your screen is the right size. And if not, then I will do maybe I will do a slider here one day, but who knows. All right, let's do some TED meshing. Grid-based is based on ftedwhile, which is a standard measure from GitHub, and there we go. It does a very good job. It just generates a very regular mesh, and that's why I called it grid-based, because what it does, it just seems to generate a grid. Okay, so honestly, I don't know what they do. It's a huge amount of code, but yeah, they're doing a good job. Not much to say about that. They generate a very clean TED mesh here. You see the TED quality is 0.04, which is very good. Everything's fine. There's not much to say about this. You can bake this into the document as solids. I'm not going to do that because that's just heavy, and this will just clog my document with a huge amount of breaths. But people keep me asking, so how do I put it into the document? Well, then just use this button here if you want to see the TEDs, and if you want to take them apart one by one and see that they actually do fit together. And if you enjoy that experience, then this button here is for you. Right now, the TED mesh is really just a conduit. So this went very well. Let's try another solid. I'm not gonna use these ones here. Let's go through the standard solids here. So you clear the old one, then you stage a closed solid by first selecting it. hitting the stage button, choosing your meshing strategy, and then hitting OK Mesh Stage Solids. And there you go. Yeah, they are doing okay, but not perfect. So one can increase the mesh resolution a bit, and then it gets better. And then you see, well, what they do here is that they run into very small angles here because they run into the North Pole here. So for this thing to work, I do have to pass on a surface measure. So there are a few TED measures right now on food4Rhino, which just wrap open source TED measures for you. So there are a few out there, and but all of them just have to mesh first. They have to first generate the surface mesh, and then you run into these kinds of problems here. Okay, if we used a Rhino 7's quad remesher, we wouldn't run into that problem. But still, the idea is that with TRmesh, which is a native mesher sitting directly on top of the Rhino C++ API, you don't run into this problem at all, you see. So this problem just disappears, because when I program against the Rhino C++ API, I can directly do distance queries, and then I can apply a blue noise meshing strategy that walks along layers and then generates a point cloud in such a way that the Delaunay mesh will turn out nicely. And then I remove TEDs outside. So basically, that's how it works. Let's just maybe also do the cone here, because the cone is the most drastic example of a geometry where the UV coordinates here run into a singularity. So with fted while buff. This is a very bad mesh here, so one can't use it for finite elements. And probably there are some settings that inside fted while that I didn't know. And then that problem would be solved. But well, my message is that with the fuzzy mesher, if you just try to match the geometry, match the volume, not exactly, but only approximately, you don't run into that problem at all, right? So then you can, okay, maybe we should increase the resolution a bit. Then the problem with the singularity at the top will just disappear. So I'm also not always exactly hitting the geometry here, but in this case, I think it works pretty well. By the way, TED meshing is really hard. And if you want to read a bit about it, I recommend reading some pages by David Epstein. I'm going to put that link into the discourse category, where he shows examples of geometries that just by mathematical reasons can't be meshed. So this is a phenomenon that does not exist in 2D. In 2D, you can turn everything into mesh, right? But in 3D, there are cases where this is not always possible for mathematical reasons. Maybe if you have time after the talk, after the official part, we can have a look at that website, because it's really fun and really interesting to see. And I'm going to show you that page by David Epstein. But right now, I'm not going to talk about this because this will lead us too far away. All right, so this is the basic idea here, that TRmesh just works by distance queries. And then there's also, so let me do this again. Okay, I'm running out of time, but I'm basically already finishing here. So let's decrease the resolution a bit. Let's do a little coarser. So I like this good old MFC interface here. I think I was the only one last year doing an MFC plugin. It was a lot of fun. I really like the MFC user interface. paradigm here. So now the resolution is very coarse, so of course we don't hit the volume very closely, but there's a remesher here, and the idea is just try to match the volume in a coarse way. And when you say, okay, the volume is described, the features of the volume that you want to describe with your finite element analysis or geometric analysis are captured. Once the volume is well described by the TEDs, then you can hit remesh, and then you can increase the resolution and remesh the existing TED mesh. So right now the volume is not very well captured because of these protruding dents here, but still you can see that, well, remeshing is of course not going to heal that situation, but the remesher is a finite element remesher that will generate meshes that are very well suited for finite elements, but also very well suited for isosurfacing. All right, and once you have a good mesh, well, you just hit that button here, bake mesh to doc for TRfem. And then, buff, what you get is an actual mesh with that you can, which is a bit of a miracle, because at first you might think it's horribly invalid because the mesh faces have 4 indices now. So if we try to draw this here in, so let's delete the ugly cone. If we want to draw this in wireframe, okay, so I have disabled all other previews other than wireframe. When you look at what this thing is in the object properties, then the display mode wireframe is baked directly into the mesh. And please don't do shaded because you're not going to see much. All right, so this is just looking ugly. You don't see much. So just leave it the way it is. Just leave it at wireframe here. Why can't I go back? Well, anyway, and don't know why I can go back. Anyway, so this is how the entire TED mesh is represented as an ON mesh. And yeah, let me make this one for now. And this is what then happens in the original example that we started with. So now in the last minute, okay, 1 more minute. What I did here was I did a box here around it. All right. So something like this. And then I mesh that box with something like this. There we go. I hit the bake mesh button. Then I make sure that this is invisible because it doesn't look nice. So before isosurfacing, TED meshes always look ugly. Okay, so that's it. A matter of fact, they're not there for beauty. Only after isosurfacing, after putting scalar fields or after putting solutions on them, then they become nice and useful. So don't look at these things here and think that this is a design or art or anything. No, this is really just there as a background, as geometrical infrastructure. And now this GHX file here can be used in such a way that we just reference just the usual mesh here. And let's not use this one. Let's use the one let's just use the coarse mesh. And let's turn this one off here. Don't need this one. And so this is this mesh. Yeah. All right. There's this one. Can turn this one off. And there we go. So I hope that you followed along. And now it should be clear what's happening here. The deconstruct mesh is actually the Grasshopper's inbuilt deconstruct mesh. You have vertices, faces. Then you have a scalar field. The scalar field is done by closest point queries. So this is very standard things here. There is the scalar field that we modulate with the sliders. And then the important thing from TRmesh is really just this one here, which isosurfaces, and that's it. So yeah, I hope what I said makes sense. And yeah, well, looking forward to your questions. Thanks for listening.
Excellent, Matthias. Very nice webinar. Amazing technology. I think very useful in some market segments. Maybe not understandable by all Rhino users, but we have a few experts here on the chat, like Aaron Porterfield, René Medel, Gersh Baderer, Mertzat Samadi, David Ratten. Yeah, there are a few questions. Simon Forhammer, he said he joined late the webinar, and it's a bit generic question. How does TRmesh compare to Dendro? You know the Dendro plugin?
Yes, I know the Dendro plugin. Well, Dendro is basically also based on a voxel engine, basically. So I think this is much easier. I think so. Maybe people think this is I'm wrong, but all you have to do to make this happen, well, just share this little mesh here, so and save it in a 3DM file. This is so simple and easy. So which mesh is it? It's here, this one here. Looks a bit ugly, but that's all you have to do to share it. And then you don't need any other plugin, maybe other than TRmesh. But a voxel engine, imagine trying to write a plugin that saves a voxel, a whole voxel hierarchy inside 3DM. This is horrible. I mean, okay, Dendro is awesome. But it's a different, at the end of the day, you want to isosurface them, right? So if you have volumetric information, at the end of the day, you do want to slice them into isosurfaces, right? If you already have TED meshes, then you already have edges. You hit them with the isosurface and chop, you get faces, triangles. It's just how discretization works in 2D very well. We just make meshes because we want to render things. We send the mesh over to the graphics card. We don't send voxels to the graphics card. So I'm just extending the idea of meshes to 3D. And voxels are also great, and I love it, what they're doing, but I think TRmesh is very simple. So, but I think this is a very long, very subjective thing. Which one is easier here? So I think it's easy to just share this mesh.
Okay, thanks. Then there is another question by Aaron Porterfield. He asks if TRmesh can create adaptive meshes, and how does it handle small corners, small features like corners?
Well, it's not. I'm not yet. I have not yet done the UI UX necessary to increase the TED mesh resolution. The meshing engine can do that easily, but it's just the UI UX problem. How do I tell? Then I wouldn't need a background TED mesh, which indicates the density field. So something like this is just a UI UX problem. So Aaron, if you have an idea how to how your data comes along, how you can tell my plugin where you want the mesh to have higher resolution, no problem. So it's really not a problem. It's really just a UI UX problem. So far, it's not yet in the 291 version, but doable. And as for corners, well, it's the same. Well, to resolve corners, if it doesn't resolve corners, so I showed it with a here this cone that usually maybe a bit after trying, but usually it resolves this the top here, the tip of the cone very nicely. But I think it's the same question, right? So then you also want to, if it doesn't work out automatically, then you want to increase the resolution near the tip of the cone. So I think it's also the resolution question. I don't yet automatically recognize that I need a higher resolution in a certain area, because I can't. That depends on the user. So there must be some UI UX thing, but it's doable. So if there's an idea how to do this UI UX thing, then I will do it. Thanks for the question. I appreciate it.
Well, Aaron also asks if you have tried TGen or MMG tools instead of TED-Wild.
Well, of course, yes. MMG is not a mesher. It's just a remesher. So they are really proud of not doing TED meshing at all. And they also say, yeah, just use TED-Gen to generate your background mesh, and then we will remesh. Well, actually, my remesher is MMG. So this button here is MMG, the remesh button, okay? So I'm using MMG here, and I'm also citing them on the license and so on. So there, and you can replace the DLL with your own DLL. So I'm obeying the LGPL license of MMG here. Yeah, MMG is cool. So this is MMG, but MMG does not mesh, it only remeshes. And as for TED-Gen, well, TED-Gen is one of those external meshes, right? It's an open source mesher. All you can do, well, on the one hand, there's a serious license problem with TED-Gen. Don't want to go into these law aspects and so on, but anyway. And then the second thing with TED-Gen is that, well, you have to mesh. You first have to do the surface meshing. This is an additional difficult step, and you can't do the distance squeeze. Then you can only do the distance from your surface mesh. So TED-Gen has its own kind of BREP format, which is very cool, but Rhino is the BREP king here. TED-Gen has no curved surfaces. TED-Gen has no. TED-Gen only has BREPs that are flat surfaces. Yeah, and so what TED-Rhino, for instance, does, well, it just meshes, and then it pretends that the surface mesh is a TED-Gen BREP. And I think that's a clumsy way of working. I think meshing has to be done directly, natively on top of the Rhino API, instead of first doing surface meshing and then pretending the surface mesh was a BREP with flat faces. That's kind of, well, I think you get what I'm saying.
Thank you again. And we have the last question by David Ratten. He says, can you give us some examples of values beyond temperature and torsion that could be approximated with TED meshes?
Well, stress states. And since I think Rhino can be used much more in high performance engineering, every scalar field that represents a measure of how overused, that represents the degree to which material is excess material in topology optimization. So in topology optimization, excess material is removed, and then people do the FEA again. So they are always based on a measure of on a usage measure. I forgot the term that Karamba uses, but Karamba puts stress states into something that they call usage, or that they have a term. Karamba has a term for the degree to which a certain volume element is an excess volume element. But I think, yeah, topology optimization is a great example. Then, yeah, the temperatures, stress states, and then, of course, when we talk about CFD, then there are others. But yeah, then there are distances, and then there are, of course, modulated distances. So everything that you generate from modifying freps. So we talked about ntop, right? And ntop has all these intricate gyroids. And how do they modify them? How do they model with them? Well, they represent shapes basically as the zeros of functions, and then they modify the function, right? So I think that's the best answer to that question. The scalar field just represents the values of that function in the sense of the frep that ntop uses, if that makes sense.
Okay, many thanks for all your answers, Matthias, and for a great webinar again. And thanks also to the viewers. Again, this webinar is being recorded, so if you miss any part of it, just refresh the page or go to the food4Rhino webinars YouTube playlist. And yeah, it was a pleasure. Hope to see you soon, Matthias. And probably next time you'll have some news to share. And again, we'll be back in a few weeks with other webinars. I still need to announce, but you will get this by our regular blog posts, in news, etc. So have a nice day and see you soon.
Thanks for watching, and thank you, Carlos. Bye, everyone. Just drop
Bye-bye.
in for questions.
Bye.